can jump in and get started. So we are going to be talking about moisture management and gas sampling conditioning. Gas sample conditioning. See if I can get this to work. Okay, just brief of what we're going to go over, just introduce the team. We have, if you hear a voice coming out of the speaker, we do have a phone a friend in here today. So we'll go over some CEMs applications and really where we're going to focus on those applications, common moisture management issues, Nafion technology, which is the technology we use at Perma Pure and the principles of how it works, practical applications of our Nafion products, and then just a bit about our company and some Q&A. Just an introduction. So our phone a friend is Nate Inkrote, who is the general manager. Perma Pure is broken up into different markets and different segments. So we're all on the environmental, scientific, and process side of Perma Pure. Laura, who is here, is our business development manager, and I'm the product manager of the ENS side of Perma Pure.
Very nice to meet you all virtually.
Yeah, the booming voice. So just to go over some CEMs processing techniques, I'm not going to go into great detail. I am sure you all are more familiar than I am with these, but obviously there's in situ, there's continuous sampling, dilution extraction, there is direct extractive, both hot, wet, and cold dry. And where we're really going to focus today is on the cold dry. That's where we're going to spend most of our time. That's where our products are primarily used, or in the cold dry extraction. I say primarily because we are surprised sometimes where our products end up and where they're used. So I never rule out any application. We work with so many customers and so many different different applications, but primarily when it comes to CEMs, especially, we're in that cold dry extractive process. So what we hear from our customers, some common challenges that they have, especially with moisture management and CEMs, there are high operating and compliance costs, difficulty of sampling hot, wet, dirty, corrosive samples, doing that reliably and consistently, because what's coming off of those stacks is, again, hot, wet, and dirty, and just to get that consistent analysis and consistently process them for sampling is difficult. High reliability required. In that reliability, we're talking about the systems must run for a long time, so we need highly reliable systems, and then products and components that can keep their reliability. They must tolerate adverse and faulty conditions. Hot and humid conditions if installed outside of a temperature-controlled environment. And then traditional systems can require frequent preventative maintenance and high repair costs. So these are all common challenges that have been reported to us. And we'll talk a little bit about some of these different techniques about moisture management and then how our Nafion products can work either alone or beside them. So here are some common moisture removal techniques. We have our Perma Pure Dryers, which we'll go into, thermoelectric coolers, water traps, desiccant dryers, gas dilution systems. I'm not going to go into each and every one of these. Specifically, mostly when we're talking about in this application market, thermoelectric coolers or the traditional means of moisture removal. But water traps, desiccants, gas dilution, they all have their positives and negatives. Water traps people are really familiar with. They're easy to use, but they can't really achieve your sub-ambient humidity levels. The stuff that you're condensing out is full of, can be corrosive. You're not just taking the water out, you're taking everything out of it. Desiccant dryers, they can get really dry, but it's not consistent because as the desiccant pulls moisture out, its performance gets more and more unreliable. It'll take the analytes out of it. And so we're really going to primarily to talk about these moisture removal technologies. We're really going to focus on thermoelectric coolers and our Perma Pure dryers, but just wanted to talk in other applications or somewhere along the system, others might be used like water traps, desiccant dryers, gas dilution systems. So I just want to imagine a scenario about a thermoelectric cooler where there's a change in operating conditions. The cooler can't react quick enough to that incoming gas sample. So then the gas is not fully condensed, or worse yet, the cooler fails completely. That corrosive condensate lands on the optical bench of the analyzer. And that damages the analyzer, the sensors. That's expensive maintenance costs plus downtime. And so this is definitely not a talk that's going to bash thermoelectric coolers. They have their place in the market. They're part of our portfolio. We use them. They're a tried and trusted piece of equipment, but with all technology has its limitations. So they can be overwhelmed if the flow sample rate conditions change. There can be catastrophic mechanical failure leading to expensive damage to the analyzers. They operate to a dew point of 4 degrees C, which is the industry standard, but they can't really get lower than 4 degrees C, and we'll discuss some reasons why you might want to get lower than 4 degrees C. They do require to be an air-conditioned enclosure or your CEM shed, which increases operating costs, and there's lots of space requirements as well. And they can have high SOx and NOx losses, which reduces the accuracy of the reading. So I'm just going to take here a half a step back and just talk about Nafion itself before we talk about any of the technologies. In basic terms, Nafion is a Teflon backbone. It's Teflon that has an occasional side chains of another fluorocarbon that end in a sulfonic acid. So it's really that sulfonic acid group that you can see at the end that does the work and separates it from Teflon. So what it does, it removes water by a first order kinetic reaction. And that's actually a chemical reaction that it's doing. It's not microporous. It's not, the water isn't filling through isn't permeating through small pores. It's actually attaching to that sulfonic acid group, and through what's called water hydration, it's actually getting pushed to the other side through this chemical reaction. It transfers by differential pressure in the water vapor between the two sides of the membrane. And because of this, it's highly selective. So we'll talk about most of your analytes will stay within the sample gas because it's not going on the sides, the sides through the pores. It is that chemical reaction. And because basically it is Teflon, it has all the corrosion resistance that a Teflon product would have too. So we talk about, it's my own word for Nafion. I call it ion permeation dryer instead of, we know that there are permeation dryers, and here's just a little bit of the difference of what those two things are. So Nafion, again, as I said, is based on a first order kinetic reaction. It moves water as a water of hydration. So basically it's attaching through the walls of the Nafion. It's attaching to that sulfonic, that chain, and then it creates a light bond. And when the next water moves through, it politely moves aside, and that's kind of how it works through that water hydration, that kinetic reaction. And a typical permeation dryer functions based on molecular size. And that's a microporous material, as opposed to the partial pressure of the water driving the functionality of a Nafion dryer. And so basically what that means is in a traditional permeation dryer, there's non-specific separation. So it's not suitable for complex gas streams. You can have anything smaller than water is going to permeate through because it's just based on size. So with Nafion, it is highly selective because only compounds that have an exposed hydroxyl group are going to migrate through the Nafion. So you might have a molecule that's smaller than water, but it's not going to get through that dryer because we're not going on particulate size. We're going on this chemical reaction. I will give Laura all the credit for this slide.
Or all the blame.
But it's a pretty simple, it's a slide that really basically explains the principle of the partial pressure differentiation. So if you see on the left-hand side, we'll have 6 molecules. On the right-hand side, we have 2 molecules, and if you will, the blue line is the Nafion membrane. And because there's different partial pressure, the water on the left-hand side is going to want to migrate through to the right-hand side. So basically, it attaches to those sulfonic chains, and it migrates through until there's equal pressure. Now we're not going to have any more migration. If there is, for any reason, a molecule appears on the right-hand side, now again we have this differential partial pressure, and we're going to see the water migrate back to the left-hand side. So it's always working on that partial pressure of water vapor. So we talk about a lot in our membrane, it's really not talking about permeability, we talk about impermeability. Because all of these things that you see here, the atmospheric gases, the halogens, hydrocarbons, the inorganic acids, all the things that listed here, they don't have that exposed hydroxyl group, so they're all retained in the sample. And what we really care about here is all these ones that are now circled in red, those are your typical combustion analytes. So when you're working through and you're trying to get the reading of what's in your sample gas, all of these, which are your typical combustion analytes, are going to be retained in the sample gas because they don't have that exposed hydroxyl group, so they can't permeate through the Nafion membrane. Now on the flip side, we have Nafion permeability. So what is removed by Nafion? Well, this is moisture control, what we're talking about. So clearly in atmospheric gases, we're removing water. Ammonia has an exposed hydroxyl group, so that's going to move through. And some alcohols, DMSO, THF, also, they will be removed by Nafion. There's some other organics listed here that have variable losses. These, not all of them, but sometimes some organics in these families might be able to turn into an alcohol, and if they do, they would also be permeable and move through the Nafion. So I'd sort of be remiss if I don't talk here about ammonia, because we know ammonia is going to be in our sample gas stream, and not only is it permeable to Nafion, it's actually the kryptonite of Nafion. It sticks those channels that we talked about that are going to be, that are going to transfer the water. Ammonia is going to clog them. And although this isn't a talk about this, we talk about ammonia scrubbers. So whenever you're using a Nafion system and you're going to have ammonia, using an ammonia scrubber beforehand will help solve that issue. The ammonia is going to react in a vapor form in the ammonia scrubber, and it's going to immediately turn into a visible salt residue and stay in the ammonia scrubber, and then and then the sample gas can pass through the Nafion. So we'll talk a little bit here about how Perma Pure Dryers work. Hopefully I can get my little arrow too. So we're basically a shell and tube design. So if you imagine it, it is a shell and then it has a tube. So this middle channel here, that is Nafion, and it's surrounded by a shell. It could be we have various different materials. So you'll have your hot, wet sample gas coming in, and then we use a dry purge gas. Typically we say instrument air. There's other methods that you could do that we'll talk about in a slide or two. But you always want that dry purge gas to flow counter to the wet sample gas. And basically, if you think back, we were talking about that, and it works on that partial pressure difference. So as you have your wet sample gas coming in and your dry sample gas flowing counter, even though this wet sample gas is getting drier, the dry purge gas is always drier than that, so you can continue to have that Nafion transfer through you can continue to have that water transfer through the whole tube. So it looks pretty simple. It's a little bit more complex to set up than this, but so again, wet sample in, dry sample counter flowing, and then because there's a partial pressure difference, you're going to be transferring water. We have various designs of Nafion dryers. We call our MD series, which is one shell, one tube, and then our PD series, which is one shell, multiple tubes. And both of these come in multiple lanes, and the PDs come in multiple. You can have 50, 100, 200 different tubes. So basically, you want to do that because you're talking about your surface area. So the way this is coming, because we're permeating through the membrane through that chemical reaction. The more surface area that the water has, that water touches in the Nafion tubing, the more drying that will happen. So in our MDs, the longer the dryer, the more the drying capability. In the PDs, multiple tubes and longer lanes, that increases the drying capabilities. Our products can be used standalone. They can be used in conjunction with other products. They're actually also, our MDs can be found as OEM components inside of analyzers as well.
Yeah, I think I've seen one of these in, I think Phil and Fisher use these
Yep, they do.
in their,
Your NOx analyzer, yeah.
Yep.
oxidus, I think, and their sulfur analyzer.
There is a sulfur analyzers as well.
So basically, your hope, a lot of the talks that we've sat through here, we're talking about, it's all about the sample conditioning, right? But water can always slip through. And, this is a way to, even if after sample conditioning, if you have water in an analyzer, to continuously to knock it out, whether you use it post whatever, say you're using it post a thermoelectric cooler or internal analyzer, you're just getting the driest gas that you can. So I just want to go over really quickly different purge gas methods. On this one on the top, we talk about that's instrument quality air, so that's coming in, and that's kind of the gold standard that we talk about. But knowing that's not always available to everybody, there's other different methods. So vacuum with ambient air, the limitation there is the ambient air, you're going to be able to dry as the ambient air is. So if the ambient air isn't all that dry, has a lot of humidity or moisture in it, that's the purge gas always must be drier, obviously, than the sample gas. The caveat being, although it's not the typical use of the product, if you wanted to humidify gas, our dryers can then become humidifiers, and it just works the exact opposite way. And then the bottom method, we have a reflux method where if you take the exhaust of the gas analyzer and that's just returned back in as the dry purge gas, or the split sample method, which is probably the most common that our customer use, works a lot like the reflux method, except for they're taking what's returning back in as the purge gas is actually coming. It's just a dry sample coming right out of the dryer. So there are just a few performance factors that, they're not even all listed here. There's many different things. One of the things, the reason I have this slide up here, chemical composition, pressure, incoming dew point, surface area, flow rate, ambient temperature, they're all going to affect the outlet dew point. So it's not really necessarily a plug and play. You just get a dryer and you plug it in and it works and you dry. There's a lot of factors, what length you might need, because all of these things, what size tubing you might need, what diameter you might need. All those things play into the performance and the outlet dew point. So as a company, we can certainly help, and through our rep groups too, certainly help figure out what's the right dryer for your applications. This is a performance curve just of our PD dryers. So you can see down here, we have 50, 100, and 200. So it's either 50 tubes, 100 tubes, 200 tubes. And then different lengths on the performance curve. What I want to show here mostly is that at our length, at the highest flow, so you can see we can even get up to flow rates of 40 liters per minute. At our highest flows, we can still reach that industry standard of 4 degrees C. But what's really impressive here is we go to lower flow rates, we can get down to dew points as low as -45. And that might not be typical for a CEMs application, but there can be some application where where you want to get that low. And so we talk here about longer tube length, lower flow rate, increased surface area. All of this is the dwell time that the sample gas is spending in the tubing. That's all going to play a factor of what your outlet dew point can be. But again, perfectly capable to reach that industry standard, more than capable to get far below that industry standard. So these are common water vapor saturation temperatures. Oh, that's a tongue twister. So if you go here, this might be your typical 70 degrees C. You're gonna have 30% water. That might be typical of some hot, hot wet stuff coming right off of the stack. 10% water can be very common for natural gas combustion. You have your thermoelectric outlet dew point, again, industry standard, 4 degrees C, 0.8% water, removes a lot of water. But our Nafion tubing can take that same thing and bring us down to -18 degrees C at 0.12% water. So it's removing over 80% water left by a cooler. So we're going to just get into a few brief things of why that might matter, why you might want to go that low. If you have things like SO2, O2, and then you combine them with water, and the water is still present, you can form sulfuric acids. If you have some, NO2, SO2, again, sulfuric acids plus NO. And also if there's some ammonia in the system and you have ammonia and SO2, SO3, and you have water, you're going to form those ammonia salts. So again, as much water as you can pull out the system, it's better. It's obviously, and it's going to be better in the long run for the analyzers. So just some benefits of drying the CEM sample to a lower dew point in the vapor phase. So why would we want to go below 4? Well, we talked about that retention of water soluble analytes. So you're going to keep your SO2, your SOx, your NOx, your chlorides. We can make accurate measurements under 50 parts per million possible. And all of this, when we talked about getting forming that sulfuric acid, acid and those ammonia salts. This is all about protection of the analyzer, maybe even more important to people, some people, than, retention of the analytes. We know that we're measuring the analytes, but we also know that our analyzers and all that equipment is expensive. So if we can reduce the acid mists, if we can reduce condensation on the analyzer bench, that just protects the analyzer. It eliminates damage to the analyzer and the system components, the sensors. It stops clogging of the line. And it also has the potential to solve many application issues stemming from the presence of water. So there can be some spectral interference, some peak drift. So those different measurements, if you have water present, can interfere with that. And removing as much water out as you can, just make sure that you get that really accurate analysis. So here's, again, talking about polishing of a gas with a PCD dryer. So you have your smokestack, and if you imagine you have your smokestack, and then you have your sample gas coming down into your thermoelectric cooler. Some water drops out of that. It continues on. And for the most part, for many people, it continues straight onto the analyzer. But like we talked about, there's still water in there, and it can have all those negative effects on the analyzer and on the analysis itself. So a lot of people, as good practice, run that through a PD dryer. So the PD dryer is taking even more water out in that vapor phase. And now you're passing into the analyzer a dry gas sample, as dry as it can be, into the analyzer. And there's a lot of versatility in the Nafion systems. So we have our MDs and our PDs that we talked about. They're used standalone. They're used in conjunction with thermoelectric coolers. They're used as OEM components within analyzers. And then we have our own systems ourselves. So here on the right-hand side is our hybrid thermoelectric cooler. It's actually not a thermoelectric cooler, so it's a hybrid cooler. It's going to function like a thermoelectric cooler, but it runs without electricity. It runs on compressed air. So just to get into a little of that, and this is our last slide, but just talking about, again, the versatility. So it's a PCD, but now it's our hybrid non-electric cooler. So it's a passive system. It requires no electric current at all. It's ideal for sites that have limited to no access to power, or other areas where a non-electric product may be desirable. So if you have someplace and you need to put some kind of cooler and you don't have electricity available there, this will eliminate the need and the cost associated with installation and permits of installing electric. So there's probably a better picture I could have put here and I should have put here, but what you can see is this is actually, if you can see the tubing running around the outside of it, that's actually just Teflon tubing. And it's running through compressed air and basically and this is under vacuum, and we're running under an inventory effect. So it's just going to kind of run through this sample to kind of cool out. It's going to condense some stuff out with a coalescing filter. And at the end on the right-hand side, if you can see here, it's going to go through basically a PD dryer. So it's really simple. There's no moving mechanical parts. So it's going to be lower maintenance costs, increased reliability. Again, just because it's just a really basic, simple design. It can be stack mounted or it can be mounted outside. The caveat being that, which would eliminate the cost of heated lines, but the caveat of that stack mounting or mounting outside is it has to be in ambient temperatures that are above freezing. So probably not good in the north, but in the south, it might make a lot of sense. Which could also save rooms in a crowded SEM shed. A lot of that we've heard recently from our customers is that their SEM shed is just crowded. There's no more room in there. And it does utilize that Nafion technology. So it has better performance, the ability to reach lower dew points than a traditional cooler. And again, so this is coming out shortly. We'll be introducing this shortly. So
We already have a version that Emerson is using in India and Mexico.
yes, we do. We do. So actually the next two slides I have are just a little bit about the company. So I probably would step out if there's any questions, any questions anybody has, I can take those questions. It can reach lower dew points than a thermoelectric cooler. So on this one, flowing about ambient temperature at about 5 liters per, again, so we're going to do comparative, right? So at ambient temperatures, about 5 liters per minute, it's going to reach -5. And We're going to, we haven't done tests yet at higher flow rates, which we will be doing in the future in possible iterations of it, but it reaches about -5.
How big is that?
It's maybe, I don't know, like, I wish I had the actual, it's yay big. Yay big, 12, it's about 12 pounds, yay big, you know, tiny, yeah. And then the thing that's nice about that is, again, so there, I mean, we won't say there's no maintenance, but it's less maintenance. And so maybe over the course of time, you're going to want to replace that PD dryer. And that's really going to be dependent on,
Does it require clean instrument air?
so it should be clean instrument air. Yeah. So, because,
What are the ramifications of it?
so dirty air, what's going to happen, you're going to get, it's probably more if it's oil-based than particulate-based, but if it's oil-based, it's going to actually cover, it's going to coat the Nafion. And so what we talked about, that increased surface area. So if you coat the dryer with the oil, basically you're decreasing the surface area, so you're not going to be able to pass
So
it
you
through.
need one of those for the air.
Exactly. Yeah, exactly. We can do that, right? Yep.
But it's not an off-on process, just like with ammonia contamination. It's a process over time. So you'll shorten the life. All of these things have a life before basic maintenance. Anyway, but, so you'll shorten the life. We can't tell you how short it will be because it really does depend on the contents of the air itself.
Right.
But that's the result. You'd still be able to make take readings for quite a long time.
So it's basically a vortex flow what you got created.
So it works similar to like a vortex cooler, except for it's running on compressed air. It doesn't have some of those like complex, you know, a vortex cooler is a little bit more, I don't know the whole technology, but a little bit more complex in it. But basically what you're going to have is you're going to have your sample gas. I have a flow diagram. So your sample gas coming in here, yeah, and you have like the vortex, you're creating that Venturi effect.
Right.
And then it's going to travel around this tubing, and it's going to cool down.
Right.
And it's going to go into a coalescent filter, and it's going to drop some water out. And it's going to travel around this tubing again. And then what's going to happen is that incoming hot sample is going to heat the sample that's coming out of the coalescent filter back up. And then you're going to go through the PD dryer, and then you're going to the outlet. So the difference here between a vortex cooler, some of the ones we studied on the model, and this is that this it is
How often does a coalescent filter need?
what was that?
How often would that filter need to be changed? Coalescent filter.
Yeah, I guess it's just going to depend on, you know, so that's the maintenance really is going to be the filter. And that really is just going to depend on the sample gas coming in. But this runs on much less air than a typical vortex cooler. Much less. So this is, I always get it's,
Nate, do you have the numbers?
it's 100 liters per minute. It's like 10 times less air than the vortex cooler. 65% less air than the vortex cooler. So.
Yep. Yeah. The vortex cooler is about, sorry, I know I'm the voice overhead. It's the vortex cooler uses about 10 cubic feet per minute. And yeah, this is a vastly lower number. I think it's somewhere in the realm of, it's in the liters per minute. So it adjusts a little bit based on flow rate, but it's a small fraction of the amount of air, which reduces the operating cost.
How fast, how long does it take you guys to get down to -5 what? -5 Celsius?
Yeah, -5 Celsius.
So for me, or
I'm sorry, what was the question?
How long does it take?
Yeah, I was saying, yeah, so you guys are getting down to -5 inside that -5C inside that chamber?
Yeah, the outlet dew point will be -5C.
Oh, okay.
Yeah, outlet dew point will be -5C.
I'm thinking real time.
Yeah. No, the outlet dew point is -5C. Yep. And so the incoming flow rate is about, so if you're running at ambient temperatures, 5 liters per minute is your incoming flow rate.
Okay.
And I think it's 3.5 cubic feet per minute that ours runs, and the comparable vortex cooler is about 10. So the operating cost is far less than this on this one. We're happy. We are just finally. So if anyone wants information, we're happy to take your information down and send you the information that we have on this as well.
On the PD dryers, what's the manifold that you guys tie all those tubes together with? How are you guys taking, I'm assuming multiple tubes are tied together, and then, so your sample limit comes in.
It's an epoxy-based header that we put them.
It's a epoxy-based header?
Yes.
Okay. All right.
So Nate, if you want to give a more technical answer to my epoxy.
Sorry, I heard Laura's response. I didn't hear the full question though.
How do we make a header for the PDs?
I'm just more curious about what's,
Oh, all right,
what do you have to watch out for from a sample standpoint?
Most applications don't run into any aggressive chemical compatibility issues.
Okay.
If you have specific concerns, we can check
Got
them.
it.
But for most applications that we run into in this market,
Okay.
we have compatible options.
Got it. Yeah, that's my question. I've used the PD or the NB, not the PD.
So the MD way gets long and it gets coiled, so the PD is, multiple ones and obviously can run at higher flow rates and fluid.
Our flow rate's less pressure.
Yep.
No, but it's shorter. Yeah, I like the
Yes.
idea of shorter, so.
Yeah.
From an analyte standpoint, what else comes out on your ammonia dryer or your ammonia removal system before it goes in that? Do you have to watch out for any analytes that are gonna get dropped out? If you know you got ammonia,
Yeah.
you now throw in another filter in front, so I'm just curious.
So it has, I think it works with a phosphoric within the ammonia scrubber. So that acts with the ammonia itself to create the ammonia salt.
Okay.
So I think because that media reacts with ammonia, that's what's creating the ammonia salt. So as long as nothing's going to react with that, then it wouldn't. Yeah.
We tend, when we're working with Nafion, our claim to fame is being able to work with water while it's in the vapor phase. The ammonia scrubber does require a little bit of liquid water present to maintain that chemical reaction. It's very small, but if you get down to very small amounts of analytes that you're trying to detect, if you put an ammonia scrubber in there and the analytes are water soluble, you may have some issues there. Again, it doesn't come up very often, but there is a little bit of liquid water present in the ammonia scrubber.
Yeah, unfortunately, I'm working in the sub-PPM range, so that's why I was curious on this question. Okay. So that even at trace levels, it's basically a reaction you guys are doing something on. Okay.
Yeah.
Any other questions?
I did just poke on to a spreadsheet to look at the flow rate requirement. So the utility for the PCD or the hybrid cooler is 3.5 liters per minute, whereas the vortex cooler is 10 cubic feet per minute. So it's, I don't know the exact calculation is, but it's somewhere in the realm of like 2% of the airflow that's required for our device versus the vortex cooler.
And then just wrap up because just a little bit about who we are as a company. So basically, Perma Pure is a part of HAMA, which is a global group of companies working towards a safer, cleaner, and healthier future for everyone every day. And so Perma Pure, we do moisture control both in the medical, scientific analysis, and environmental analysis. And then we have Max Tech, which is oxygen sensing and delivery, primarily in the medical market space. So just again, just for the Perma Pure side, in our medicals, you can see in the medical and where we do, but where our products are found a lot. And that's why I said, a lot of times it's our typical is our 4-degree C dew point, but you can find us in ambient air monitoring, a bunch of scientific lab analysis, CEMs, research and development, process control, environmental analysis. So if there is a need for moisture management in anything you're doing, there's a chance that we can help. Just that you give us that opportunity to do. And that is it. So thanks so much for your time. Yeah, if you want to give us your information, we can, if you have a card, we can send you information on that hybrid cooler if you